Hello, calculus fans. Going to make a video about mixing problems. This is for people in Calculus 2. This is I'm making this video in the fall of 2024 as I teach Calculus 2. I told everyone in class I would do a few more examples. We finished the last class with an example of these mixing problems. This page right here is from one of my review sheets. You can find on my materials page where I summarize the different applications we do. But mixing problems, what's nice about them is we're not really assuming very much. You don't have to know hardly anything from other sciences. The model is just we're trying to measure. So typically Y is the amount of some substance, a pollutant or contaminant or salt or something in a lake or a room or a vat. So in our mind, it's this and something's coming in, but it's really any closed system. Like if you want to study, something in the air and you have vents coming in and going out in a particular building. Or if you want to study the pollution in a given lake and you know that there's one river coming in and another river going out. These are all the same situations of you have some closed system you're trying to measure. And you're just going to figure out how many in our problems, it's mostly how many kilograms per minute are coming in and how many kilograms per minute are going out. And the main reason that this ends up being a differential equation is because the amount that's coming out typically depends on how much is in there at the given moment. So this important expression, as I said in class, is Y over V. That's the concentration at a given moment. And I'll do some of these problems. Anyways, most of the problems, the flow in and flow out is the same. And the flow is usually given in like liters per minute. So typically what happens in these problems, before I dive in, I'm just going to say some generalities and then I'll talk a few problems. Typically what happens in these problems is you have some sort of what I would call the concentration, kilograms per liter. Like someone scooped out a little bit of what's coming in and said, okay, it appears that for every liter, there's so many 2 kilograms or something. And then you have a flow that's liters per minute. So you often have two numbers you have to multiply. You'll see this in the problems. Two numbers you have to multiply, 3 kilograms per minute, 2 liters per minute. But the key information there is 6. Every minute, 6 kilograms go in. On the way out, the concentration is changing. And so this is changing, and sometimes the volume is changing too, the volume of the tank. Most of the problems we do in Maths 125, the volume's constant, times the flow. So that's how these problems go, and I'll do these in these problems. But basically, you just figure out how many kilograms per minute are going in, how many kilograms per minute are going out. That will depend on Y. The units can help you, all this stuff I say here. We often ask about long-term behavior, but let's dive into a problem. I actually did this one in class. It's a lot of information to take in, but really if you want to step by step, identify the volume of the tank. That's what this is. And when you go to set up your differential equation, typically you have these 4 elements. So we'll talk about slight variations on a theme, but just to keep things simple from now. So you have this flow in, and you have this flow out, and you have this concentration in, and you have this concentration out. And you want kilograms, in this case kilograms per minute, to come out of this, and you want kilograms. So I always found this when I was a student and didn't quite understand what was going on. I found it helpful to realize, okay, I'm trying to get kilograms per minute. So where the liters comes in is right here. It's this L. L. It's this V right here. I said L because of liters. And the amount of salt that's going to be in the container is changing. So in this problem, a few visuals. Sorry, I've kind of jumped right in. But in this problem, what they tell you is that it's a 12-liter vat, and the amount of salt that's in there at a given moment is changing. And so the current concentration is Y over V, and we know the volume is not changing. And the reason we know that is because the flow in and out is the same. The flow in is 3 liters per minute. The flow out is 3 meters per minute. So let's put those things in there. 3 liters per minute. 3 liters. This is liters per minute. This is liters per minute. This right here is kilograms per liter. And so that takes care of it. The other one, in this case, it says pure water. The fact that it says pure water is telling you there is no salt in this. And now we got it. So in this case, you would say dy dx, or dy dt, is 0 minus, and then we could simplify this, y over 4. And the initial amount of salt is 7. That's what's up here. Then you can solve. And this one's separable. So if I was doing this, I probably would divide both sides by y. 1 over y dy is negative a fourth dt. And then we switch gears into solving mode. Maybe I'll do this quickly. This is log of the absolute value of y is negative 1/4 t plus c. And we've done this a lot in class. I talked about how it's this kind of same 4 steps. I think I have this in my written up solutions. But just quickly, maybe for this first one, and I'll spend less time on this on the other ones. 1/4 t plus c. Make sure that c is in the parentheses. Normally we clean this up and write y as plus or minus e to the c, e to the negative 1/4 t. And we've talked quite a bit. This has been our main conversation point, which is that all of this collectively is a constant, in which case it might be kind of nice to call this c1 and then just call this c. C e to the negative 1/4 t. And we've got it. And now we plug in our initial condition. So when this is 0, this needs to be 7. So C has to be 7. So the amount of salt in this container is 7 e to the negative 1/4 t. And often we ask what's going to happen in the long run. But this one's fairly straightforward. In the long run, as t goes to infinity, you're going to get 0. Okay, that matches up my solutions, and that should make sense. We're fleshing things out. So what I really would like to talk about is setup. So what changes, and I did this in class as well, I just am setting the stage, and then I'll do a couple more interesting ones. Just a recap here. So in this question, everything is the same, except the concentration coming in is 2. So if you think about how that's going to change things, let's use my same weird colors. 3, 3, we're going to do minus. It's still going to be y over 12. But this one is not going to be 0. It's going to be something else. It's going to be 2. So the main difference here is it's going to be dy dt is 6 minus y over 4. And I think the initial condition is the same. Now that does dramatically change the problem in that it's now not, there's going to be always be salt in the container. So it's actually going to approach some sort of balancing amount. The solving is very similar, except the fact that you can't easily separate these. It looks like back when I solved this, I didn't do it in an optimal way. I think now, if I was doing this, I would factor out a 4 and then write 24 minus y. That's just a matter of how I want to work with fractions. And then I would divide 1 over 24 minus y. dy is 1/4 dt, and then I'd integrate both sides. This becomes log of 24 minus y is 1/4 t plus c1, and then we play all the same games. Now in the end, you can clean up your answer. I'll make this a little bigger. This is in my notes, you can see. But in the end, I got to here. I plugged in my initial condition, so when I plugged in a 0, I got a 7, and I solved for c, so c came out to be negative 17. And then as t goes to infinity, that goes to, this part goes to 0, so you're left with 24. So this is going to approach 24. I mentioned in class that you can also tell already that the slope is going to get closer and closer to 0 as y approaches 24. Okay, so this is basically, that's where I did that in class. I just was recapping in case someone missed class, or if I use this video again in the future. So now let's talk about a few variations on a theme. So there's our summary. Maybe I'll grab it. We've now done several of those. And then let's come down here and look at a new problem. So I'm going to put it right here so we can see it. So how is this one different? Go a little bigger. Assume a 100-liter vat contains 5 kilograms of salt initially. So it doesn't hurt to draw. The picture is just more for you to have something to attach your thinking to. We go here, we go here. It's a 100-liter vat. It says that there's 2 pipes coming in. This really doesn't change things. You're still just trying to count how much salt is coming in. So let's just talk about in for a second. One of the pipes is 4 kilograms per liter times 3 liters per minute. So let's call that whatever, this first pipe here. But the important thing there is that's 12 kilograms per minute is coming in. So from this one, it's 12 kilograms per minute of salt that's coming in. The other pipe, we can multiply those two, and it's 10 kilograms. So from this one, it's 10 kilograms of salt per minute. So the total amount coming in, there was that was what was different about this problem, is you had to say 12 plus 10. And that was all part of this. So that's not a major change to the problem, having 2 pipes coming in. You just do the same thing. So this much was coming in and this much. So don't let that scare you. And then it's going out. The concentration going out is going to be Y over the volume. The volume's 100 and it's not changing. The reason I know it's not changing is because, and maybe this is something else we had to think about, was because there are 8 liters per minute flowing in altogether, and there's 8 liters per minute flowing out. So there we go. And at that point, you have dy dt equals 22 minus 8 over 100. I guess I'd divide top and bottom by 4, and I would say 2y over 25. And y of 0 is 5. Seeing that here. So yes, it's a lot of information, but it goes pretty quick. In terms of solving, you're going to solve this in a very similar way. If somebody asks me what the limit's going to be, I already know the answer because it's going to be when this equals 0. Let's go look at my solutions. Like I said, I decided I wasn't going to move this down here. Get rid of this. Let's look at my solutions from my notes. Wrote these a long time ago, probably more than 10 years ago when I wrote this example. But you can see there's our setup. You can see I separated. That was before I liked to simplify fractions first. I integrated. This is an easy part to mess up. I simplified. I got here. I plugged in my initial condition. And then if somebody asks me in the long run, I'm approaching this because the power is negative on the exponent. Okay, but I just wanted to talk about setup. Okay, let's finish with one last one. And I usually do this as an entry task for my lecture that I would have been doing, but it's the day before Thanksgiving, so we're not holding that lecture. So here we go. What's going on? Yet another VAT problem. Here we go. Dot, 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 dot. It's a 50-liter vat, but it only has 20 liters of water. Okay, that's interesting. Why did they give me these 2 numbers? It starts with 24 kilograms of dissolved salt. So I do know that y of 0 is 24. A pipe containing pure water. Okay, so that's pure water. 6 liters per minute. And there is no salt in it. So that's going to be a 0. So some of this stuff seems to be coming out not too bad. This is going to be a 0. This is a 6, but doesn't matter because it's 0. And the mixture drains at 4 liters per minute. So this is a 4. So the big difference in this problem is that these 2 numbers aren't the same. And I asked this is more of a problem for the follow-up course, but you should immediately recognize that this is a problem. What's going to happen to the water in the container? It's going to go up. In fact, we can say how much. The volume is changing. So unfortunately, this problem, this is changing. So we'd have to give a formula for it. So how am I going to give a formula for it? Well, you know that it starts at 20 liters and that you add how much? You add 2 liters per minute. So plus 2 liters, so that's 20 plus 2t. So for every minute you add 2 liters. So that was the tricky part of this problem. We don't really ask you these in Math 125 because it leads to an equation that's not separable. In this case, it is separable because this number is 0, but if this number wasn't 0, it wouldn't be. Okay, so now we're ready. dy dt equals 0 minus y over 20 plus 2t times 4. And we have the initial condition there. I think we could divide top and bottom by 2. And so we could rewrite this as dy dt is negative 2y over 10 plus t. That's separable, so I would divide both sides by y. 2 over 10 plus t dt. I would integrate both sides. You get the log of y equals negative 2 the log of 10 plus t. I guess these numbers are positive, so C1, and then you do some cleaning. So let's do that. House cleaning. You exponentiate both sides, so the absolute value of y is e to the negative 2 log of 10 plus t plus c1. So I'm just going to write e to the c1. Let's simplify that as we go. It kind of gets, it's very good to know this rule because you're going to be using it so much in these problems. And sometimes it's nice to just do that one step. So you get y is plus or minus this thing, e to the c1, and then this thing. This actually simplifies a whole bunch if you want to practice your log rules. So I'm going to call that c, but this simplifies a lot because you can bring this inside, and you can say e to the log of 10 plus t to the negative 2. And so those cancel. So all of this can be written as c times 10 plus t to the negative 2. And this happens a lot in these sorts of problems. You get y is going to be c over 10 plus t squared. So it's a very different solution than the other ones we're seeing. And a lot of the problems we've done, we're getting essentially the exact same differential equation over and over again. In this case, the initial condition is when you plugged in 0, you got 24. So we need to write 24. Don't just assume that's c. In this case, it's not. 10 plus 0 squared. So c would be whatever 24 times 100 is. So it's 2400. And so our solution would be 2400 over 10 plus t squared. So there you go. That's just probably the most challenging I could think to make a mixing problem because the volume was changing. Anyways, so there you go. There's mixing problems. Yeah, I think that's all I'll say about that. Hope that helps you. You'll do a few of these in homework. You'll see quite a few on old exams, and I hope you can come back to this because we pretty much hit every topic there. All right.